All right, let's jump right in. Today, we're going to tackle a really powerful shortcut in calculus. It's for integrating a certain type of fraction. You know, the ones that look super complicated at first glance, but, spoiler alert, have a beautifully simple solution. Seriously, if you've ever found yourself staring at a messy fraction in an integral, this is the pattern you've been waiting for.
So here's the magic formula, the key to this whole thing. The integral of a fraction where the top part, the numerator, is just a multiple of the derivative of the bottom part, well, it turns out to be that multiple times the natural log of the denominator. I know, it looks like a mouthful right now, but trust me, once you get the hang of this, it's a total game changer.
But hey, just having a rule isn't enough, right? Where does this thing even come from? And more importantly, how do we actually use it to crush some real problems? That's what we're here to find out.
Okay, so here's the plan. We're going to start with why this rule works by looking at the log rule in reverse. Then, we'll see it in action with some basic examples. After that, we'll level up and master some variations, tackle a tricky proof, use it to find the area under a curve, and finally, put your skills to the test with a final exam challenge. Let's do this.
All right, first things first, to really get this, we need to connect it back to something you probably already know pretty well, differentiation. It's all about thinking backwards, you'll see.
And this right here tells the whole story. Think back to when you learned to differentiate the natural log of some function, right? The answer was always its derivative, f prime of x, sitting on top of the original function, f of x. Well, integration is just the opposite of differentiation. So it totally makes sense that if we integrate f prime over f, we get right back where we started, the natural log of f of x. It's a perfect circle.
Okay, enough with the theory. Let's see this thing in the wild. We're going to start with some pretty straightforward examples, just to get your brain trained to spot that key relationship between the top and bottom of the fraction.
So check out this first one. Our denominator is x squared plus 3. Now what happens when you take the derivative of that? Come on, you know this, it's 2x. And would you look at that? 2x is sitting right there in the numerator. This is like the perfect textbook case. You couldn't ask for a better setup.
And since the top is the perfect derivative of the bottom, we can just slap our rule on it directly. The answer is simply the natural log of the absolute value of that denominator plus our good old friend, the constant of integration, c. See? Pattern spotted, problem solved. Boom.
But you knew it was coming, right? Problems aren't always going to be that neat and tidy. So now let's dig into what happens when the numerator is almost the derivative, but not quite. And while we're at it, we'll see how to handle definite integrals, the ones with limits.
So what if the numerator is a multiple of the derivative, but not a perfect match? This happens all the time. Take this example from the textbook. The bottom is 2x cubed plus 5x squared. The derivative of that? It's 6x squared plus 10x. But look at our numerator. It's 3x squared plus 5x. It's so close, right? It's just off by a number. So what's our move here?
The secret here is just a little bit of algebra. As you can see, our numerator is exactly half of the derivative we actually need. So what we do is we pull a 1/2 outside of the entire integral. We're essentially balancing the equation. And by doing that, what's left inside the integral is now a perfect f prime over f situation. Our constant, our k, is just that 1/2 sitting out front. From there, it's business as usual. We integrate and just make sure to keep that constant in our final answer. Pretty clever, right?
Okay, let's add another layer of fun, definite integrals. The first part of the process is exactly the same. We look at the denominator, x cubed plus 2, we find its derivative, 3x squared, and bingo, it's a perfect match for the numerator. So integrating it is a piece of cake. The only new step is that we have to evaluate our answer at the limits, from 0 to 2.
So we plug in the upper limit, 2, which gives us the natural log of 10. Then we subtract what we get when we plug in the lower limit, 0, which is the natural log of 2. So we have ln of 10 minus ln of 2. Now, don't stop there. Dust off those log rules from your memory banks. The difference of two logs is the log of the quotient. So our final, exact, and much cleaner answer is just ln of 5.
All right, brace yourselves, we're heading into the deep end now. Sometimes an integral is going to look like it has nothing to do with our pattern, at all. And that's when you have to get your hands dirty with some algebra, or, in this case, some trig manipulation, before you can even think about using our rule.
These show that questions are awesome because they're like a final boss battle for your math skills. They make you combine everything you know. At first glance, this integral looks like a total mess. It looks nothing like f prime over f. Our mission, should we choose to accept it, is to wrestle this thing into a form we recognize.
This is a multi-step mission. First, and this is the magic key that unlocks the whole thing, we use a double angle identity to simplify that denominator. Suddenly it looks a bit more manageable. Then, we pull out a really clever trick, a u substitution. By letting u equal sine squared x, the whole integral just transforms into something way simpler. Now we're talking. It finally fits our pattern. After integrating with u and being super careful to update our limits, a little simplification with log rules gets us exactly where we need to be. It's just a beautiful chain of logic.
Okay, enough of the abstract proofs for a minute. Let's make this visual. We're going to use this exact integration technique to solve a really classic problem, finding the area under a curve.
So here's the setup. We've got this curve, and we're told that the shaded area, starting at x equals 1 and going to some mystery point p, is exactly 4. Our job? Find that value of p. This means we have to set up a definite integral where the answer is known, but one of the limits is not.
Let's break down how to solve this. First, we write out the definite integral for the area, from 1 to p. Then we do our usual check. The denominator is x squared plus 1. Its derivative is 2x. Our numerator is 4x, which is just 2 times the derivative we need. So our k value is 2. Easy. We can integrate that to get 2 times the natural log of x squared plus 1. Next up, we evaluate that expression at our limits, p and 1, and we set the whole thing equal to 4, because that's the area they gave us. After that, it's no longer a calculus problem, it's an algebra problem. We just have to carefully solve that logarithmic equation to find our p.
That was a fantastic example of how all these pieces fit together, wasn't it? So, to make sure this is all cemented in your brain, let's wrap up with a quick-fire round of exam-style questions. Ready?
Okay, question 1. This is a straight-up test of the basic rule. The numerator is 3 times f prime of x, so our constant k is 3. Take a second. What's the answer going to be?
And there you have it. The integral is already in that perfect k f prime over f form. So the answer is just k times the natural log of f of x plus c. In this case, that's 3 times the natural log of x squared plus 1 plus c. Nice and simple. All right, last one. And this one is a bit of a curveball. I love it. Here, the function f of x is actually ln of x itself. Whoa. So what happens then? Well, let's just follow the steps. If f of x is ln of x, what's its derivative, f prime? It's 1 over x. So our integral is really 4 times the integral of 1 over x divided by ln of x. Wait a minute, that fits our pattern perfectly. The top is the derivative of the bottom. So the answer is just 4 times the natural log of the absolute value of our original function, which was ln of x. So the final answer is 4 times the natural log of the absolute value of ln of x plus c. A bit of a brain bender, but the rule still holds.
So before we sign off, let's just run through the big takeaways from today. Number 1, always check if the numerator is a multiple of the denominator's derivative. That's your first move. If it is, you just need to adjust for that constant k by pulling it outside the integral. When you're dealing with definite integrals, don't forget to evaluate at the limits and then use your log rules to simplify things down. And please, for the love of math, don't forget the absolute value signs and the plus c.
Look, getting this integration pattern down is a massive step forward in calculus. It's all about training your mind to see these hidden connections and turn complicated problems into simple ones. So the question I want to leave you with is this. Now that you've mastered this form, what other powerful patterns are out there just waiting for you to discover? Keep digging, and thanks for joining me.